I'm wearing my Hawaiian shirt in honor of Dave and in thanks for the many times we were able to go to Kauai. Looking forward to equally sunny and wonderful beaches in South America, hopefully next summer, right? And in the meantime, I'm going to tell you about this oxygen sensing probe we've developed. And as I looked through my talk today, quickly trying to revise it, because so much of what I was going to talk about has already been presented by previous speakers, but I'll go ahead anyway. So oxygen, well, those of us who are ancient remember worrying about oxygen as something that might artifactually shorten one of your long lifetimes in a cuvette. But at physiological levels, oxygen has little effect on short lifetime fluorescence. So we have to look for new methods to see it. But what's out there for looking at things without fluorescence? Well, the Clark electrode and Seahorse, as Suman mentioned earlier, are the sort of standard. If you have a lot of cells, you can have a look at that. Let me get rid of this, sorry. The trouble is, again, you need 1 million cells or MRI imaging. MRI is very sensitive to oxygen state, but you know, even MRI microscopes have millimeter resolution. And then there are methods that use probes of various sorts that you end up sticking into tissue. Otherwise, you can add various organic compounds. And these are all very disruptive and point measurements. They're not for imaging. And the closest one has gotten to the kind of imaging we'd like to do is phosphorescence imaging with various phosphor nanoparticles. Unfortunately, a lot of them are cytotoxic and can only be brought in by the sort of endocytosis. So they're difficult to target. But they've still, you know, been useful in showing that tumor environments are lower oxygen than normal tissue. So how do we do fluorescence lifetime? Well, I've done both phase and TCSPC over the years, but we mostly do TCSPC. In our case, we do 2 photon. So we use the MyTi, focus it in. We have a special chamber where we can control the gases that are present above the medium and the cell layer. The rest is pretty conventional, Becker and Hickel. At first we use mesh PMTs, but we've also used hybrids, and we use non-descan detection to get most of the light. And again, for every pixel, you get a log histogram of arrival times that we enjoy fitting. So this has partly been covered before, especially by Enrico, but essentially FLIM can really tell you a lot about a fret. I like to use the bucket model for Jablonski diagrams, where you do your initial excitation to the upper bucket, in this case a donor, and it's going to have nanosecond decay. But if there's a nearby lower energy acceptor, you can open up a new pipeline to fret, and that's going to drain the bucket faster. And in this case, I'm showing a sort of a blur for the fret rate because there could be many angles, many different levels of fret going on. And essentially the kind of thing that we collect where it's a time series, you just see the bucket empty earlier when there is an acceptor present and you're looking at the donor. One of the things that was alluded to earlier by Enrico is that you can also look at the acceptor if it's not dark. Oh, by the way, with 2 photon FLIM, we can actually look into live tissue. But that aside, if you are willing to look at an acceptor and look outside the fundamental circle because it has a longer phase, because it got delayed as it transited from the donor to the acceptor, you can actually pick up more information because the acceptor information is sort of orthogonal to everything else you might acquire. But unfortunately, and I'm going to be talking about a dark acceptor, so this is just an aside. And by the way, when it's outside that circle, proofs going back to 1980 show that that's the same as if we have a negative alpha in our fitting program. So what is our probe? Well, as I mentioned, oxygen doesn't do a good job of quenching normal fluorophores at physiological levels, but there are natural sensors and absorbers of oxygen. And if you've ever seen a nice steak turn gray, you know about one of them, and that's myoglobin, whose spectrum changes as it is oxygenated or loses oxygen. So we connected myoglobin to M-cherry, and with the idea that the absorbance of myoglobin is different in the oxygen and the oxygen-free state. In particular, oxymyoglobin doesn't have a very good overlap. So the distance for characteristic Forster transfer is quite long, and the lifetime doesn't drop very much compared to M-cherry alone. On the other hand, when this absorbance of myoglobin changes due to loss of oxygen, it extends a tail out in the red that creates more energy transfer. And in particular, the lifetime drops from 1.3 to about 0.93. And that's doesn't seem like a lot, but it's pretty easy nowadays with short pulse sources to see. So here's a measurement of a bunch of cells, and I'm going to jump you into it. These are average lifetimes based on molecular averages. So it's the alpha weighted lifetime, which is proportional to the number of molecules. And what you can see is, as Suman mentioned earlier, you can poison the oxygen consumption of cells with rotenone and entomycin, or you can get cells that have defective mitochondria. So either of these open symbols do not consume oxygen. And these cells then have a binding characteristic for myoglobin that climbs up in the few millimeters of oxygen level and eventually work towards some plateau that's pretty similar for both cases. However, when oxidative phosphorylation is present in normal mitochondria or in just the cytosol, you see a lower level of lifetime characteristic of it being more deoxy. So what's going on in here is consumption. And we fit the hyperbola, which is based on the number of molecules. That's why we use the molecular mean lifetime. And you get pretty similar minimum and maximum values for these with the affinity that you would expect for myoglobin. This, however, is the control. If you just put M-cherry in, and you can see M-cherry itself doesn't care what level of oxygen you have. And this sort of coincidentally also tells us that there isn't a big temperature change between full bore oxygen and anoxia in these cells, because M-cherry does have a temperature coefficient, but we're not seeing a change in lifetime here. So as Suman mentioned, different cancer cells with different metabolic potential and different metastatic potential have different rates of consuming oxygen and of moving around and all sorts of things. So since we could now measure oxygen within the cell, we could correlate that with the level of metastatic potential. So we have very fast growing tumor cells, A549. You can see they consume a lot of oxygen. You can see that HeLa cells are intermediate, and slow growing prostate cancer cells consume less oxygen. And using rotenone as a calibration curve, you can take any point, go back to that curve and down. You can correlate the extracellular oxygen to the intracellular level for these different cell types. So that's a handy tool. In addition, we can do the kind of things that Suman was mentioning just an hour ago about the optical redox ratio or the fluorescence lifetime based redox ratio of cell types like this. And using the free bound ratio of NADH, again from lifetime, you can watch how the Warburg effect of becoming more glycolytic is delayed as you go anoxic in the fast cells, where it starts to switch to glycolysis much earlier in the slow growing prostate cancer cells. So these are the kind of things that are enabled by measuring the oxygen. Of course, we wouldn't be doing imaging if it wasn't for the fact that you can see heterogeneity in the system, as mentioned before. And this is not just heterogeneity between loci and different cells, but also between organelles if we target. So if you shut off the oxidative phosphorylation, you see a lot more of these blue levels, which indicate high oxygen levels in the cell. And you can make any of these cells go to anoxia if you take away their oxygen. Then they become more orangish, again, short lifetime deoxy. But mitochondria are always a bit more anoxic than their counterparts. And so there are gradients on the order of microns in cells. And this is totally contrary to prevailing wisdom about how fast oxygen diffuses in cells. There are some who believe that you can't even form a few millimeters oxygen gradient over 50 microns. Now, we've done some simulations that show that over about 8 microns, you can get several millimeters of heterogeneity, but this is still controversial. So we had some worries about this. And there are a lot of things you have to think about, as Dr. Day mentioned earlier, about how to trust your fluorescent protein construct. Oh, by the way, these are pixel mean lifetimes, just showing how mitochondria are typically lower, indicating more deoxy. So what are our worries about these probes and the things that we've been attacking the last year or two, trying to eliminate every possible artifact we can? Well, hemolysis was our biggest worry, because you take away the heme, you can't bind oxygen, there's no FRET. And going back to that M-Cherry control I showed you, M-Cherry alone wasn't that different from oxygenated. It was about 1.4 nanoseconds versus 1.33. So that's not, I mean, it's certainly, 5 or more times the standard deviation, but it might be hard to see a little bit of hemolysis if it were present. We had 2 solutions to that. One is we have another probe that I'll be telling you about soon using EYFP. But I think the ultimate improvement in this is something that Dr. Day mentioned earlier, and that is there's a better probe than M-Cherry called M-Scarlet, which has a longer lifetime that would stretch this difference and make any hemolysis more apparent. We also worry about Z gradients in unstirred media above the cells. And what we're working on now is getting a plasma membrane targeted version of that so that we can put the probe right down on the surface and not have to worry about what's going on in the media above. Index of refraction is a lifetime shortening effect. And so there are certain organelles that have higher index of refraction. Peter So does a lot of work on index of refraction in cells, if you want to study that. But by getting rid of myoglobin and putting the probe in the very same place, you can look at M-Cherry itself and see that that's not a big effect. Aggregation, as Dr. Day mentioned, is a real problem in some of the red proteins, but George Patterson who is a great loss to us, by the way, in the last few months, assured me that M. Cherry was not going to aggregate at the levels, the micromolar levels that we were dealing with. One can also vary transfection levels with leaky promoters or use the transfection for different amounts of time before observing. From a question you heard me asking earlier of Dr. Day, denaturation would be a worry if the chromophore were present in some altered form in lysosomes. That could show up as a contaminant. So I was very relieved to hear that's not a big problem except for one of the turquoises. And maturation should affect intensity, but as David and Enrico and the rest of us have all been reassuring you, Lifetime cares about an intensive internal structure and not the amount. So those are the ways we've been attacking it. This is just showing how the probe that we use to measure medium oxygen has a certain physical extent, so we worry about Z gradients and how we want to put probes right on the surface. So there's another worry I didn't mention, and that is myoglobin takes on a different state in the presence of reactive oxygen or nitrous oxide contaminants or nitric oxide. And that is, there's the oxy and the deoxy state, but MET myoglobin, the iron 3 state of myoglobin that can be generated by reactive species, has more absorbance in this red part. And therefore, the lifetime, which I told you more overlap is a shorter lifetime, might even be down around 0.6. And again, that's not too different from 0.9, and it might show up as a contaminant. So our concern about that is one of those things where one person's grant application is another person's artifact, and vice versa. Reactive oxygen species are traditionally studied with various actinic probes, things that accumulate in a cell and change color, or otherwise act like radiation badges in the sense that they show you that something's accumulated, but they don't image its accumulation in situ. And there are many sources of reactive oxygen in the cell, especially including the mitochondria themselves that leak a little bit in their electron chain, and they produce reactive oxygen species. And of course, there's a whole clinical industry of intentionally making reactive oxygen species, like phototherapy. I won't read to you the reasons for this, but I should also mention that NO, which can be a side effect of reactive oxygen species, is also a signaling molecule that's important for maintaining things like our blood pressure. So we'd like to be able to measure this as well as see it as an artifact for our probe. And there are various ways that MET is formed. Usually it's just a direct oxidation process from deoxy or from oxy. But there are various ways to go through CO or through NO to get there. I won't read this to you. I'll be providing the slides to the file later. So what did we decide to do? Both to defeat the worries we had of an artifact and to try to develop an ROS NO sensor. Well, we looked at other fluorescent proteins, and we noted that EYFP had a spectrum that's sort of in the middle of this changing region of oxy-deoxy. And I was talking with Alessio, who left our lab a couple years ago to go to Davis, and I eyeballed this and said, I bet that overlap, when you properly integrate it, hasn't changed. And sure enough, he calculated an R0 change of about 1% between oxy and deoxy. But met in that region actually becomes less overlap. So it goes opposite what we saw in M. cherry, in that the lifetime would get longer for met instead of shorter out in the red. Now, EYFP alone is about 3 nanoseconds. And if you were to put these all together, EYFP would have about the same lifetime in oxy and deoxy. In other words, it's a don't care probe for oxygen, but it would have a lifetime, we guess, around 2.5 for met, which would be a distinct signal. So I've indicated that here with arrows indicating strength of fret. EYFP would have similar fret from either oxy or deoxy states and a weakened transfer from met. So short lifetimes, long lifetime. M. cherry would have a very short lifetime for met, a short lifetime for deoxy, as I've shown you, and a fairly long lifetime for oxy, almost the same as M. cherry. Oh, let me back up a second. There's another nice thing about this. For those of you who don't have labs with FLIM, although FLIM is getting cheaper and easier to use every year, this offers another opportunity. If you don't have MET present and you just change the oxygen level, EYFP won't change its brightness. It isn't changing lifetime, it isn't changing fret, it's going to be about constant. So it serves as an internal ratiometric standard for the change that you would see in the brightness of M. cherry. So it's a way to bypass FLIM for labs that don't yet have FLIM and still measure oxygen. Again, I'm a physicist, not a biologist. I leave it to those who are really good at this to discuss the way that myoglobin is regulated within cells. Again, I'll put this into the slides, but there are a lot of ways that MET is consumed and generated. And in particular, there is a reductase activity that we can take a preliminary look at. And its job is to basically, well, it's one of the cytochromes, and it basically gets rid of any MET, restoring the myoglobin that you want and need to use in the cell. So experimentally, we wanted to benchmark this new probe. And the way we did it is to put in known amounts of NO and unknown but linear amounts of reactive oxygen and known amounts of oxygen in various fast-growing non-small cell lung cancer cells. And then we correlate that with what we've measured, and then we look at that freebie that we get out of it of doing a FLIM-less ratio to get oxygen. So this is just looking at a correlate of putting in reactive oxygen species or NO, either through a sensitizer that you illuminate called 2CAD that generates reactive oxygen, or a S-nitrosyl octoguanosine, which breaks down and makes NO. So we were just looking first at internal proteins in the cell to see that they get carbonylated. And that's something that you do with another fluorescent probe, bodipihydrazine. And we could see that we were definitely generating RO and NO in the cells, because you can quantify these things in that actinic method. And you can do a standard curve to find out how much NO you're creating. That's all done with absorbance. And here's an example of what we can do just using lifetime of that combined probe. If you put a scavenger in there so there's no MET at all although this is very similar to normal cells, you see that there is a short lifetime characteristic of oxy and deoxy. But if you put in saturating levels of NO, or you illuminate the RO generator, you definitely can detect it as the lifetime moves up to the middle twos. And if you were looking at EYFP alone that didn't have the sensor on it, it would be way up around 3.1. So when one looks at this, you again get some sort of hyperbolic behavior. You move from a radical free environment up into, it doesn't take a lot of NO, and you get to the middle twos of the lifetime, which indicate exposure and the generation of MET. Same is true when you use a sensitizer, and you have controls where you've removed all free radicals, kept it down at 1.6 or up at 3.1. Okay, so here's that optional ability, and I discourage avoiding FLIM. FLIM is wonderful, whether you do it with harmonic methods, the fast FLIM box, TCSPC, whatever flavor you like, FLIM is great. But for labs that might not have FLIM, as I mentioned, you can get an internal standard based on the yellow fluorescent protein, and you can just use the ratio of intensity versus oxygen to get a sense of the oxygen content in the cells. We haven't pushed it much further except to show that this tool is available. As I mentioned, we did just tickle a little this possibility that the myoglobin reductase acts to detoxify and remove the MET form of myoglobin from the cells. So what you see in the black bars here are the normal EYFP lifetime behavior. And you can see that it doesn't take a lot of SNOG to generate NO and to produce MET. But it's a bit delayed. If you poison that reductase, you can see that it comes on even earlier. So what must be happening at these lower levels of NO is that you're generating this material, but the reductase is taking you down to here, and similarly here. And that's pretty much true no matter what the imposed oxygen level is. Poisoning the reductase reveals that there is a fair amount of activity at low levels to remove the MET. And the fact that things are pretty similar out here tells you that we've overwhelmed that reductase activity. As Suman mentioned, the optical redox ratio and its analogs using free bound ratio are very useful in watching cells move from more glycolysis to more oxphos and vice versa. Generally Warburg in tumors to more glycolysis, but oxidative stress also can lead to that. And you can see that here by our looking at the free bound ratio in cells that were treated with the nitro group. And you probably also heard both Lionel and Enrico talking about how to add DC light to obtain absolute alphas in the phasor plot. It comes, in our case, in TCSBC, by normalizing the sum of alpha tau to the total intensity of a steady state measurement. But we also obtain absolute molecular alphas for the free and the bound quantity. So you can independently watch if your ratio is changing, whether that is due to, in this case, no change of the free amount versus a depletion of the bound material, or in the case when you're doing a sensitizer making RO. These reactive species do not change the alpha-1, alpha-2 ratio. And in this case, they're both being depleted by the oxidative stress. So all of these things are available to us. I think, our main view is oxygen is such an important partner of metabolic behavior that we wanted to see not only the side indicators, the battery acid of mitochondria responding to oxygen. We wanted to see the oxygen itself, and we wanted to see the harbingers of oxidative stress at the same time. So, one little thing about these absolute numbers of alpha. Dave very early on talked about how Professor Weber wanted to look at the public life of molecules. I'm afraid I've been digging into the private life of nearly non-fluorescent molecules lately using picosecond lasers and upconversion. And what we found is that this actually underestimates the amount of free NADH. That folded conformation that Suman showed you contains about a third dark molecules. And so when we eventually get to absolute numbers of molecules for biochemical modeling of enzymatic reactions, we're going to have to say that these have to be inflated for free, about 30%. By the way, we made it a three-way probe with EYFP and mCherry both attached to myoglobin. But if you don't want that dual capability, EYFP myoglobin alone, just a simple dimeric chimera, does just as good a job of finding responses to reactive oxygen stress or NO. And we get similar results with and without the poison propylthiol uracil treatment. I didn't draw the lines in here, but again, you can see that inhibiting the reductase leads to that kind of behavior. So I'm not going to read conclusions. I'm just going to say we have a dual purpose probe, oxygen and reactive oxygen. We can avoid FLIM for those who really need to. Met myoglobin is really important in regulation of various signaling. And we only took a crude initial look at reductase activity, but we look forward to doing a better job of that in the near future. Significance, we don't know of other imaging of MET, which has a lot of importance. And we hope it becomes, more interesting, and especially we're glad to disseminate these constructs to people who are interested in these kind of metabolic studies, and we hope to see a lot of that.